then silver iodide. Okay, which is correct for silver iodide? Do you memorize all of this? Like the colors, the precipitates. So we're given this reaction, and in the product side of the reaction we have silver iodide, so that means that one is the precipitate, so it is solid. Okay, how do we know the color of the precipitate here and the solubility? Okay. So what are the properties of silver halides? What are those silver halides? Silver chloride, silver bromide, and silver iodide. Okay, check this. So for silver chloride, this produces a white precipitate. This is soluble in ammonia. So say dilute ammonia. And then for bromide, silver bromide, this has cream precipitate, soluble in concentrated ammonia. And then we have silver iodide, which has a yellow precipitate, but this one is insoluble in ammonia. Okay, so which one here is correct from the choices? Yellow. Okay, we only have two choices that have yellow, A and B, but it says insoluble, so the answer here should be letter A. Our precipitate here is silver iodide. Do you still remember how to solve for atom economy? Percent atom economy? Okay, so that would be the molar mass of the desired product divided by the sum of the molar masses of a total or sum of molar masses of the reactants times 100%. Alright. So we're given here the molar masses of the reactants and products. So for sodium iodide, the molar mass is, molar mass of sodium iodide is 149.9 grams per mole. And then silver nitrate, molar mass of silver nitrate is 169.9, and then molar mass of sodium nitrate, that is 85. Then molar mass of silver iodide is 234.8. Then we just plug in everything for the percent atom economy. Okay, molar mass of the desired product, that one is the total of our desired product here is silver iodide, right? So silver iodide 234.8 divided by the total molar masses of the reactant. So that is 149.9 plus 169.9 0.9. So that is 319.8 times 100%. Okay, 2. This is equal to 73.4%. So this is the percentage atom economy by mass for producing silver iodide. So from the choices here, we have 73%, so we can round this off to just 73%. So the answer here should be letter D. No questions on with aqueous potassium hydroxide. 11A. What type of reaction occurs in this preparation? Addition, elimination, reduction, substitution. So what type of reaction is this? When you react chloroethane and potassium hydroxide. What is chloroethane? Chloroethane, 2 carbons. So that is CH3, CH2, then chlorine, right? And then potassium hydroxide, so we have hydroxide, KOH, hydroxide. Then this would produce hydroxide, to produce alcohol, H2OH, and then chlorine. Okay. So in this case, the hydroxide ion, this one, notice that the hydroxide ion replaces the chlorine atom here. Yeah. Originally we have chloroethane with chlorine, and then when it reacts with potassium hydroxide, the hydroxide ion replaces the chlorine atom. The chlorine here in the first compound, chloroethane. So it produces this product. Okay. So this is like substitution, right? Nucleophilic substitution. Substitution. Okay, we only have addition, elimination, reduction, substitution. Or you can just simply answer substitution. So from your paper, that one is letter D. Then for letter B, how do the boiling temperatures of ethanol and chloroethane compare? And what is the reason for the difference? Okay. Okay, the answer here from your paper, it's letter A. Yeah, ethanol is higher, has higher boiling temperature, and the reason is ethanol molecules form hydrogen bonds. Yeah, because the ethanol here has an OH group, so the molecules form strong hydrogen bonds. While chloroethane, this one only has one dipole-dipole. So ethanol has high boiling temperature. Then for the next one, letter C, bromoethane and chloroethane react with aqueous hydroxide at different rates. Which is correct? Okay, bromoethane. Okay, bromoethane. This one is halogen, right? Halogen alkane. And then we have potassium hydroxide. So it produces alcohol. for 11C, okay, bromoethane, chloroethane, reacts with hydroxide. Okay. So this is halogen, the halogen alkane, and then potassium hydroxide. So this produces alcohol. The same reaction, because this is the same reaction. So this one is a substitution reaction. So that means the rate here depends on the carbon bond strength, or whatever that is produced there. Okay, so reason difference in rate. Bromoethane is faster, bromoethane is slower. Carbon to bromine bond, carbon to, okay, let's check the bond strengths here. So we have carbon to chlorine bond. So this has like approximately, from the chart, what's the bond value for this in kilojoules per mole? Like 300 plus, maybe 300 plus kilojoules per mole. And then for a carbon bromine bond, is approximately like 200 plus kilojoules per mole. Therefore, this bond is weaker than bromine bond. So that means weaker bond means easier to break, and that means the bromoethane here reacts faster than chloroethane. So bromoethane reacts faster than chloroethane. So let's take a look at the choices. Bromo reacts faster. So we have two choices that says bromoethane faster, A and B. Let's check on the reason. Carbon bond is weaker. It should be weaker. So the answer here should be letter B. Okay. What's this? Butanol completely burns in oxygen. So we have, okay, butanol, C4H9OH. Okay, and then oxygen produces carbon dioxide and water. Okay, the molar mass of butanol is 74 grams per mole, and the molar volume of gas at room temperature. Okay, molar mass of C4H9OH, that is 74.0 grams per mole. Then molar volume at room temperature and pressure is 24 cubic decimeter per mole. 7.4 grams, okay, mass of butanol is 7.4 grams, was burned completely in 16.0 cubic decimeters of oxygen. So we're given the volume of oxygen, which is 16 cubic decimeters, and the mixture of gases produced was cooled to room temperature and pressure. What is the final volume of the mixture of gases in? Okay, so we find the final volume of the mixture of gases. Right. Okay, since we're given here the mass of butanol, we can calculate for its number of moles, molar mass and mass. So we divide the mass. Okay, mole butanol, C4H9OH. This is just 7.4 grams divided by 74.0 grams per mole. So this is the number of mole of butanol, 1.00 mole butanol. And then from the equation given, the reaction given, we have 6 mole oxygens per mole of butanol, right? So we need 6 moles of oxygen per mole of butanol. So we can get the number of moles of oxygen here. That's the ratio. So we can multiply this by the mole ratio. So mole butanol, C4H9OH, times the mole of oxygen. So we can get the number of moles of oxygen per 1 mole butanol. And this cancels out. So that is 0.600 mole oxygen. Okay. Then so we already got the number of moles of butanol, and then we got the number of moles of oxygen. We're given here, what's this? The volume of oxygen. Volume of oxygen is 16 cubic decimeters, and then we have the molar volume of gas at room temperature. Yeah, I think this one is the mixture of gases initial volume of the mixture of gases. So let me delete this. Okay. So we get the moles of oxygen, initial number of moles. Initial number of moles from its volume, which is 16 cubic decimeters, and the molar volume, which is 24 cubic decimeters per mole. So we just divide that to get the number of moles. So 16.0 cubic decimeters divided by 24.0 cubic decimeters per mole. So this is just 0.667 moles oxygen. Okay. So the initial number of moles of oxygen is 0.667, and the one that we calculated, the number of moles of oxygen that is needed in the reaction is this one, the 0.60. So we can calculate for the excess oxygen here. Excess oxygen left after reaction, so that would be 0.6667 minus 0.6. So this is just 0.06667 mole oxygen. And now we can calculate for the number of moles CO2 produced. Yeah, so we can get the volume, because what is asked here is the final volume of the mixture of gases. So let's calculate the number of moles of CO2 produced. Okay, from the given reaction, we have 4 moles CO2. Yeah, we need we produce 4 moles of CO2 per mole of butanol. So CO2 produced, so there are 4 moles of CO2 per 1 mole or mole of butanol. Okay. So we can just multiply the number of moles by the mole ratio, moles of butanol. So we already got previously the number of mole. We calculated the number of mole of butanol, which is 0.1 mole butanol. Multiply this by the mole ratio of carbon dioxide and butanol. That one is 4 moles carbon dioxide per 1 mole butanol. So this is 1.1 times 4, so this is 0.4 mole carbon dioxide. Right, and then we can calculate total number of moles. Okay, so we already got the number of moles of carbon dioxide produced, that is 0.40. Then we can get the total number of moles of gas at room temperature and pressure. So that means CO2, moles of CO2 plus the excess oxygen. Because there is an excess oxygen, because we only needed 6 moles of oxygen. So there is an excess of we only needed 0.6 mole of oxygen, and there is an excess of 0.0667. Okay, so the total moles of gas at standard at room temperature and pressure is just the sum of the produced carbon dioxide gas and the excess oxygen gas. So that is this one, 0.40 mole CO2 plus 0.0667 oxygen. So this is 0.4667 moles. So this is the total number of moles of gas at room temperature and pressure. And now we can calculate the final volume. So the volume here, we can just multiply that by the given volume, molar volume of gas at room temperature. So we multiply that 0.4667 mole times 24 cubic decimeter per mole. So this is just, I'll calculate that, 11.200 cubic decimeters. So this is now the final volume of the mixture of gases in at room temperature and pressure. So from your paper, the answer should be letter B. Okay, so now we are asked for the final volume of gas in cubic centimeters. if the final mixture of gases is passed through a U-tube containing sodium hydroxide. Okay, all right. So passing the gas mixture through sodium hydroxide. Let me write this down. Mixture through sodium hydroxide, and this one removes the carbon dioxide. Removes all the carbon dioxide. So that means it only leaves the oxygen that is unreacted. So leaving only the unreacted oxygen. Okay, so we calculated earlier that the excess oxygen we calculated that one is equal to 0.0667 mole. And the molar volume, given the molar volume of gas at room temperature and pressure, that is 24 cubic decimeter per mole. So we can now calculate the volume of the excess oxygen. Yeah, what is the final volume of gas? Yeah, it should be the excess. So volume, final volume is the volume of the remaining oxygen. So we just multiply the excess number of moles of oxygen times the molar volume of gas, which is 24 cubic decimeter per mole. So that is 1.6 cubic decimeters, but we are asked in cubic centimeters. Can multiply this, then we get 1,600 cubic decimeters. From your paper, the answer is letter B. Okay, then no questions on this. Okay, we're on number 13. A halogenoalkane is dissolved in aqueous ethanol. When aqueous silver nitrate is added, a white precipitate forms immediately. What is the halogenoalkane? Okay, so we need to write that, the reaction. Okay, so what is the significance of aqueous silver nitrate here? When aqueous silver nitrate is added, so the test with aqueous silver nitrate, this one detects halide ions. So this can be released when halogenoalkane undergoes hydrolysis. So the white precipitate should be silver chloride, right? So halogenoalkane plus ethanol. Dissolvent. When aqueous solvent is added, okay, and then you add silver nitrate. So what would be the this produces a white precipitate. So we need to determine this one, the halogenoalkane. Okay. For silver nitrate, then we have ethanol. Then that means this produces silver chloride. Yeah, because it's white precipitate. We've discussed this in the previous problem. We have sodium chloride, silver chloride, silver bromine, no, silver bromide, silver chloride, and silver chloride produces a white precipitate. So this should be silver chloride, this one. Okay, so how do we determine now the halogenoalkane here? This one that is dissolved in ethanol. Okay, the fact that the precipitate here forms immediately, so that means the carbon, whatever element bond here, that means that this is more reactive. More reactive, that means the bond is weaker, right? Weaker, more reactive. So how many halogenoalkanes are there? They have like, let me check. Primary, secondary halogenoalkanes. Let me check if we can. Okay. Okay, so we have primary, secondary, tertiary. So only that. So okay. So primary, secondary, and tertiary halogenoalkanes. Classification. So which classification here of halogenoalkanes dissolves in ethanol and produces a white precipitate that is silver chloride? So let's identify each one of this. So the primary halogenoalkanes, the carbon, okay, so the carbon bond here is attached to one carbon atom. So the general formula, let me just write the general formula of this. So okay, and then for the secondary, and then for the tertiary, okay, so attached to one carbon, this one is attached to two other carbons, and then for the tertiary, attached to three other carbons. Okay, so but in this case, in the given problem, since the white precipitate is formed here, so this immediately means that the carbon bond here, as what I said earlier, is weaker, therefore more reactive under these conditions. Then the typical type of or classification of halogenoalkane in this case, yeah, because we have chloride there, so it should be tertiary. So the answer should be tertiary. And now we don't have tertiary in our choices, so we check here which ones from A to B is tertiary. Okay, so we have option A, we have chlorobutane. Chlorobutane is primary, right? Chlorobutane is primary because the carbon here is carbon chlorine bond is attached to one other carbon atom only. So that one is primary. And 2-chlorobutane, this one is secondary. In letter C, 1-chloro, 2-methylpropane. Okay, propane, methylchloro. So this should be secondary too. No, primary. And then we have option D, 2-chloro, 2-methylpropane. So you have 2 chlorine and then 2 methyl. Okay. So how many carbons there? 3 other carbons. Propane. Okay. I'm sure A, B, C, they are not. So the option should be letter D. And that is also the answer in your paper. So you need to identify first if the reaction is, if you are asked for halogenoalkane classification, you need to identify first whether it is primary, secondary, or tertiary. And then if you're given options like this, you need to identify also this one, the specific compounds as primary, secondary, or tertiary. Okay, we're on number 14. Propanol CH3, CH2, okay, and propanone are isomers. Which mass charge peak would not be expected in the mass spectrum propanone? So how do we get the peak here? We have propanol, CH3, CH2, CHO. Then we have propanone. This is a ketone. So CH3. Okay. So we need to compare the mass charge ratio for this. Right. Okay, so for CH3, then we have CH2, C2H5. Okay, so let's compare first for CH3, this one. We'll see. CH3. This one and this one. Okay, so the mass per charge for CH3. What is the mass per charge for CH3? E3. Mass of carbon and hydrogen. This is 15. 12. 15, right? And then for the C2H5 fragment, that is 12, 24, 29. So this is 29. Okay. And then for C2H3O, we have C2H5 and then C2H3O fragment, or C3H7. So that is CH3 4, oxygen 16, 24 plus 16, so that is 43. And then for the mass charge for the molecular ion or the propanone, we can just get the molar mass of propanone. So this is just equal to the molar mass of propanone, which is 58. Okay, the question is, which peak would not be expected in the mass spectrum of propanone? So we're only asked for propanone. So this one, the CH3, that one is present in both propanol and propanone. We're only asked for propanone. This one is present in propanol, not in propanone. So we don't have here. So CH3, we don't have H5. We have C2 but no H5. And then for this one, this is for propanone, present in propanone. Okay, present. And this one is, okay, this is for propanone, present in propanone. So the question is not, so the one that is not expected in the mass spectrum of propanone should be this one, the mass charge ratio of 29. So the answer here should be letter B. The answer in your paper is also letter B. Chemical test, which pair of observations is correct? Okay, from your paper here, it says letter C, warm with acidified potassium dichromate. So the first one, warm with filling solution, no change, red precipitate. Letter B, add solid phosphorus chloride, no change, misty fumes. Letter D, add sodium hydrogen carbonate, phases and no change. So the answer should be letter C. Okay. For letter A, it's not an answer because it doesn't give a positive result with a filling solution. While letter B, okay, this is chloride, solid phosphorus chloride. So neither propanol nor propanone contains hydroxide group. Check. Okay. Check first. So sodium hydrogen carbonate. So you have to identify each of this, the different tests, the filling solution and the potassium chloride, potassium dichromate, and sodium hydrogen carbonate first. So filling solution, that one is for aldehydes. Potassium chloride, I'll just write that down. So for filling solution, aldehydes like propanol, so aldehydes here are oxidized, so produces a red precipitate. Then ketones like propanone, no change. Okay, and then for letter B, potassium chloride, phosphorus chloride, both aldehydes and ketones here. Both these are, we're only given aldehydes and propanol, propanone. Okay, Yeah. Phosphorus chloride, this one is only for hydroxide group. Hydroxide groups, such as alcohols, acids. So neither aldehyde nor ketone reacts to give misty fumes. And letter C, we have acidified potassium dichromate. So aldehyde here is oxidized. And this the solution turns green. Then for ketones, no change. And for the last one, we have sodium hydrogen carbonate. Okay, so only acids here release CO2. Only acids release CO2 or fizzing. None of the aldehydes and ketones reacts. So the answer should be letter C. Is it letter C? Yeah, turns green and no change. The enthalpy change for the conversion of anhydrous copper sulfate to the hydrated copper sulfate can be found using Hess law. So that is CuSO4 solid plus water. Okay, enthalpy of the reaction. H2O. A student carried out experiments to determine the value of the enthalpy change. Known masses of anhydrous and hydrated copper sulfate were dissolved separately in water in insulated containers, and the temperature changes measured. Okay, the results are shown in the table. Justify Y volumes. Okay, we don't need to calculate this. State why different volumes of water are used into. Okay, calculate the enthalpy change of solution. Enthalpy change of solution in kilojoules per mole for anhydrous salt copper sulfate. Assume that the heat capacity of the solution is 4.2 joules per gram. Heat capacity equals 4.2 joules per gram per degree Celsius. Then density of solution is 1.0 gram per cubic centimeters. Okay. So we're given here the mass of copper sulfate, which is 8 grams. The volume of water is 50 cubic centimeters. Density is 1.0 grams. So that means this is volume. Okay, so we can get the mass of water from here, the density and volume of water So the mass of water is just equal to 50 grams. Then temperature change, delta T. Delta T here is 16 and negative 3. Solution. P negative. Oh, this is only for anhydrous, so that is 16. So 16 degrees Celsius. Okay. And then heat capacity. Alright, so now we can solve this. Q equals mc delta T. So mass is 50. Okay, mass of solution, forgot. So mass of solution here should be the mass of an anhydrous copper sulfate, which is 8, plus the mass of water, mass of copper sulfate plus mass of water. So this is 8 grams plus 50 grams. So this is 58 grams times the heat capacity, which is 4.2 joules per gram degree Celsius, times delta T, which is 16. Right. What is this? 58 times 4.2 times 16. So this is 3,897.6 joules. And then we can solve for the molar mass, number of moles of copper sulfate. Really screenshot. A number of moles of copper sulfate. Okay, so that would be the mass of copper sulfate, which is 8 grams, divided by its molar mass. So copper plus sulfur plus 4 times oxygen, that is 159.6 grams per mole. So number of moles is 0.501 mole. Okay, now we already have the number of moles of copper sulfate and the heat release. So now we can solve for the enthalpy change per mole. So enthalpy change per mole. So enthalpy of the solution. So that is kilojoules. Released, so this is exothermic, right? Because the temperature change is positive, so that means the solution is warmed up. So this is an exothermic process. So this one is negative. Right? So we need to convert this to kilojoules. So this is just 3.90 kilojoules. So this is just negative 3.9 kilojoules divided by the number of moles, which is 0.0501. Okay. 3.897. Oh, this 3.897. We'll just round it off later. 97 divided by 0.50501. So this is approximately negative 77.78 kilojoules per mole. Let me check from your paper. From your paper, the answer is negative 66. Oh, I miscalculated it, so it should be 33. Sorry, should be 3360 or 3.360 kilojoules. So this should be negative 3.360 kilojoules divided by 0.0501 is negative 67.07 kilojoules per mole. So this one is within the range, so this one is acceptable. We just have to subtract here. So enthalpy of change of the reaction is just the enthalpy of change of the solution for anhydrous minus the enthalpy of change of the hydrated solution. So we got 67 there. Negative 67, negative 67.0 minus what we have here from the table. 12, okay, 12.6. So this is just negative 79.6 kilojoules per mole. Okay, we're on 15D. Hydrates of sodium carbonate may be represented by the formula Na2CO3. Okay, we don't know the number of moles of water molecules. The value of X can be found by making up a solution of sodium carbonate and titrating this with a solution of hydrochloric acid of known concentration. A known mass of sodium carbonate and water was dissolved in water, made up to the mark in a 250 cubic centimeter volumetric flask and mixed thoroughly. 25 cubic centimeters portions of the solution were titrated with 0.09 mole per cubic decimeter hydrochloric acid using methyl orange indicator. The mean titer was 25.6. Okay. The equation for the neutralization reaction is sodium carbonate plus hydrochloric acid, then sodium chloride, carbon dioxide, and water. Calculate the amount in moles, okay, number of moles of sodium carbonate. Sodium carbonate, the amount in moles of sodium carbonate in 250 cubic centimeters of solution. Let me check from your paper. Okay, that one is confusing. Okay, the first thing we do here is we solve for the number of moles of hydrochloric acid per given 25 cubic centimeter of a liquid. Yeah. We have this. Okay. 25. Okay, 25 cubic centimeters portion of solution were titrated. So it's just, okay, it's just portion. So we get the number of moles of HCl, hydrochloric acid, per 25.0. It says portion aliquot. So we convert that first 25.0 cubic centimeters. We convert that to cubic decimeters. This is 0.02560 cubic decimeters. Okay. And then 0. 0.09. So 0.09 mole per cubic decimeter. So we get the number of moles here. This is 0.002304 mole hydrochloric acid. And then from the given reaction here, equation, 2 moles of hydrochloric acid react with 1 mole of sodium carbonate. So moles of sodium carbonate in 25 cubic centimeters, we can solve for the number of moles of sodium carbonate in the aliquot. That is, we multiply by the mole ratio. 0.004 HCl times mole ratio, that is 1 mole sodium carbonate per 2 moles HCl. So that is 0.001152 mole sodium carbonate. Okay, well, it says here that the 250 cubic centimeter flask contains 10 such aliquots. So the total moles here will be multiplied by 10. But yeah, it's 10, right? So 250 divide 25. That is 10. 250 25. So that means 10 portions. So we just calculated in each portion, so we can multiply this by 10. This one times 10, so this is just equal to 0.01152 moles of sodium carbonate in 250 cubic centimeter solution. Okay. All right, it's the same answer as in your paper. So we're on 15D double I. 15D double I. The 250 cubic centimeters of solution was prepared by dissolving 3.29 grams of sodium carbonate. Use this mass and your answer in DI to determine the value of X. Give your answer to the appropriate number of significant figures. Okay, so we're given the mass of sodium carbonate and the volume of the solution, which is 250 cubic centimeters. Let me check. Okay. So we got the result from the previous problem. We got 0.01152 moles sodium carbonate in 250 cubic centimeters. Solution. So we just get the molar mass of the hydrate first. So molar mass of the hydrate, this one, is just equal to the mass, that is 3.29 grams, divided by the number of moles, which is 0.01152. This is 285.6 grams per mole. So this one is the molar mass of the hydrate. Okay. Then the next thing we do is we get the relative formula mass of anhydrous sodium carbonate. So relative formula mass of Na2CO3, or just the molar mass. So that is 2 times sodium plus carbon 12, or 2 times 23 plus 12 plus 3 times 16. So that is 105.98 grams per mole of the anhydrous sodium carbonate. Okay, then we get the mass of water. Mass of water per mole of hydrate. Okay. Okay, so we just subtract here. So we subtract this one from here. So that would be 285.6 grams per mole minus 105.98. 285.6. So that is 179.6 grams per mole. Okay, so that is the mass of water per mole of hydrate. Then we get the number of moles of water per formula unit, because we need to get the value of X here. So moles of water, which is X, is just equal to this the mass of water per 1 mole of hydrate, which is 179.6 grams per mole, divided by the molar mass of water. That one is 18.02 grams per mole. Divided by 18.02. So this is 9.97, or approximately 10. So X here is 10. Give your answer in, okay. From your paper, it's also 10 from the calculation in your paper. But this is how to calculate it. Yeah.